So we have discussed previously that the creep deformation is a rate dependent deformation, and in creep deformation basically what happens that the atoms, they are actually flowing, and that's why the name which comes from the word creeping. So you apply a constant load and the material starts to flow, and this is a little bit of that we have discussed about the strain versus time dependence. And the strain does not remain constant in creep, and it changes with time. So once you give some amount of time, then the strain changes. So if you compare the material response, for example, to the elastic materials, then if you change the strain rate, so if you apply the same amount of strain for different times, then a purely elastic material, which is rate independent, will not show any change in the curve. So as you can see here, and a plastic response, which is highly rate dependent, you can have something like this, because of course at different stress level you will have different strain level, and if you change the strain rate, the amount of the strain can be changing, and if you change the stress, the values will also be changing. And then you can have a slightly rate dependent response of elastic plastic material. Again, in this case you see that elastic modulus is not changing because the strain rate is not very different. It is also not very close. So we are talking about a difference of, let's say, of the order of 100 or 1000. And in metallic material, elastic plastic metallic material, you will see that the elastic modulus will not show much difference. But if you change, let's say, the strain rate to 1000 meter per second or 2000 meter per second, which is done in an impact test. So in that case, what happens is that the elastic modulus will be changing. So, but if you do not change the strain rate to that amount, then the elastic modulus remains same, but the plastic part, that shows the time dependence or the strain rate dependence. So the plastic stress strain response of polycrystalline material, they usually, for the metallic material, they usually do not show the time dependence below a certain ratio of the melting temperature, where they are known as rate independent. And after a certain ratio, they start showing this time dependence, and this usually happens in the metallic material. So you can imagine this, that something, for example, let's say steel, which is at room temperature, and as you are going higher in the temperature, you are approaching the melting temperature. So what is happening is, from room temperature to the melting point, the material is going towards from solidity to liquidity, right? So as it approaches the liquidity, as it is approaching the melting temperature, because you are providing too much heat to the system, or the temperature is very high, so the atoms are vibrating more. They are getting more freedom. They are getting more amount of mean frequency to vibrate along their equilibrium positions, and this allows them to, so they have more possibility to move. Apart from that, with increasing temperature, what will happen in polycrystalline material is that the dislocations, which, so if you have n number of dislocation or slip systems which are valid at lower temperature, number of slip systems might increase as you increase the temperature. If you look at it in a different way, then dislocation movement is actually flow of the material. So you can consider it to be a laminar flow, where one layer of liquid is flowing over another layer of liquid. And this flow, as you increase the viscosity, this flow tendency will decrease, right? If the fluid is very viscous, then it will be very hard for them to flow over each other. But if you decrease the viscosity, then it may happen that the laminar flow changes to turbulent flow. So the flow becomes very easy. And so what happens is that you can have various slip systems which get activated at higher temperature. Apart from that, if the dislocations during their movement, they're getting locked, for example, let's say at inclusions or semi-coherent interfaces or incoherent interfaces, or at dispersoids, as we have discussed in the dispersion hardening, it can also happen that they get locked at the lower crotral barriers. These barriers, it is easier for dislocations to cross them as you increase the temperature, because dislocations can climb. The energy barrier to cross a dispersion, that decreases because you are at higher temperature, so you are providing already too much energy to the system. So all these phenomena will make the deformation very easy at higher temperature, and that's why it becomes time dependent. So you don't have to increase the load, so the force or the stress, the material with time itself will be flowing, because diffusion will be happening. If you remember, diffusion, it's a function of time as well as temperature. So what we have done is we have increased the temperature, and so the time dependence has been magnified. So with time, the diffusion is happening at a faster rate, and therefore the flow of the material. So for example, if a dislocation is locked at lower crotral barrier, this dislocation wants to climb. If climb is allowed, then this dislocation will cross the lower crotral barrier, right? So you know that Shockley partials. So the perfect dislocation, they dissociate into Shockley partial. They come on two different 1-1-1 plane, and then they intersect at a plane which is not 1-1-1, and then they get locked, and this is lower crotral barrier. Now, if this Shockley partial has to climb, then it can only climb by combining, by becoming a perfect dislocation, and it has to take the uh, stacking fault with it while moving. So this can only happen because there is too much energy barrier for them to combine and then to go to another plane and then start moving again. It requires some amount of energy which is available at higher temperature but not available at lower temperature. So the creep deformation is described in terms of homologous temperature. So you want to know, of course, because the 100 degrees Celsius or 200 degrees Celsius is not too much for a steel, but it is very high temperature for lead or aluminum. So we want to normalize the behavior, so we take a ratio of the temperature versus the melting point of the temperature, which is called homologous temperature, although it doesn't have any unit. So it's a ratio of temperatures using which the material's deformation can be described um, in terms of creep or time dependent deformation. So creep, as we have discussed before, uh, the creep deformation. So in this case, what is happening is strain. So we have applied a constant stress. So what is happening is that strain is increasing with time. If you apply a constant strain, for example, so you put sample in the specimen and then you want to pull it to, let's say, 5 mm only. So in this case, you are applying a constant displacement, okay? So if you apply a constant strain, what will happen is that the stress required for that much amount of strain will decrease with time, okay? Because the material is viscous, so the material is deforming with time. So instantly, the stress required to achieve that much amount of strain will be very high. But if you allow some time for the material, then for the same amount of strain, the stress required will be decreasing. Okay, so if you keep the strain constant, then the stress decreases with time, and if you keep the stress constant, the strain increases with time. So the first one we understand conventionally as creep, and the second one is called stress relaxation. Okay, and of course the third one shows if you change the strain rate, then what happens to the plastic flow. So if you increase the strain rate, usually the strain hardening is higher, and if you decrease the strain rate, the materials gets softer. So as I said, the role of diffusion at higher temperature is very important, and diffusion controlled mechanisms will be governing what kind of deformations are happening. So as we discussed, dislocation climb will be very important phenomena. Concentration of vacancies are important for dislocation climb, because that is what we call non-conservative movement of dislocation, where vacancies provide the mechanism for the dislocation to go on a higher plane. Then we also discussed that new slip systems can be activated at higher temperature. Another phenomena which we did not discuss is grain boundary sliding. So what is happening is there are two grains. So it's a three-dimensional structure, one grain. So there are two grains and they are in contact. The boundary between these two is an amorphous part. It's a high energy part where atoms do not have any configuration. They do not follow any constraints of being on a plane, because there is no definition of plane. So that part we understand. With increase in temperature, this high energy area is getting more and more energy. So the flow, we know that even at room temperature, the substitutional atom and the interstitial atoms are always diffusing more, but substitutional atoms also have a higher diffusivity at the grain boundary, because they do not have to necessarily find a vacancy next to them so that they can diffuse, right? Because in grain boundary there is no requirement of having an atomic site, and so a vacancy is not required so that you can move. The atom can move very easily, so the diffusion is very high on the grain boundary already. If you increase the temperature, what happens is that this grain boundary acts like a liquid, because the atoms are now moving with a even higher velocity. So then these two grains, which were actually in constraint at lower temperatures, at higher temperature they can move. Okay, so these grains, they can actually rotate. Okay, and this boundary can move. So this is called grain boundary sliding, and this is also again diffusion controlled phenomena which affects the material's performance. So we will see that dislocation climb we have already discussed. Grain boundary sliding is a mechanism of creep which happens at comparatively higher temperature. So if you are at comparatively lower temperature, the major mechanism which will be responsible for the creep behavior in the material will be dislocation climb and new slip systems getting activated. But if you go further higher in temperature, then grain boundary sliding becomes the major phenomena which controls the creep deformation. Apart from that, if you go higher in temperature, the surface will be getting oxidized. So oxygen is always available around us, because that's how we breathe. And this oxygen can, it usually even react at room temperature with steel, for instance, and that's how you get the rusting in steel, and the other alloys also make oxides over it. So for example, aluminum will have a layer of aluminum oxide. Usually you put chromium in steels because chromium has a higher pilling bedworth ratio, which is simply the ratio of its oxide volume. to the volume of the non-oxide form, so just chromium, which is greater than 1. So you put chromium in steel because if so, first of all, chromium has a higher affinity for oxygen. So chromium will be forming chromium oxide, and that will be given preference in comparison to iron forming iron oxide. So if you put chromium in the steel, this chromium oxide forms, and this chromium oxide has a filling bed-width ratio of more than 1, so it covers the whole surface, so no further oxidation of the steel happens. These phenomena happen at room temperature. Now if you are at higher temperature, these reactions, because we have decreased the energy barrier by going at higher temperature, if you remember Arrhenius equation, which looks like this. So although this is the equation for diffusion, but the kinetics of the oxidation process will also follow Arrhenius equation, which will have an activation energy, and you will have the rate of oxidation equals to some constant into exponential of minus activation energy divided by R into the temperature. So it will follow the similar kinetics. So if you are at higher temperature, then oxidation becomes very easier. If you are in oxidizing environment, if you are in some other corrosive environment, for example, if you are in sea, or if you are in let's say sulfur is more in your environment, then that sulfur will be reacting with the surface. So oxidation is a prime problem when you go in higher temperature, and sometimes you can have corrosion also. So these processes, they combine with the creep process, and they make it more detrimental for the material to perform. So the material will fail very easily. So why? Because there are two mechanisms now. First is purely creep, and second is there is a corrosion. So once you have a crack, for instance, and you have oxidation at the crack tip, then the crack will propagate with a higher velocity. So the material resistance will decrease because of this corrosion. So this is why initially, when people used to do fracture mechanics test, they used to put dye at the crack tip, right? Because you want to know from which point to which point the crack has increased. So they used to put a dye, and then the crack has increased, so you know that this was my initial point, because the dye will color, it will mark the initial position, and then you know the final position, so you can find out what is the crack length. But this method of crack measurement was banned because this dye creates a corrosive environment, and it influences the material crack velocity. So by applying a dye, we are actually tampering with the material's properties, and that's why this was banned. So corrosive environment also plays an important role in creep. So these are some of the things which we will be discussing. Of course, we have discussed about creep rate in very basic in a schematic, but we will be looking at the creep test in more detail. So here there are some important information. For example, for ice melting temperature is 0 degrees Celsius, right? So creep for ice will be happening at even lower temperatures, so negative temperatures. So at minus 50 degrees Celsius, you can find that the ice is creeping. And this is very important in avalanche studies. So in glaciers, for example, because in glaciers you have layers of ice over ice. And those layers, because let's say the lower layer of snow in the Greenland or in Iceland or in the polar areas, the lower layer of the glacier has more pressure from the layers which are hanging on that, right? So there is a stress applied on it, and that stress is coming because of the weight of the layers which is above this lower layer of glacier. And so there is a stress, and because the temperature is sub-zero in the polar areas, so the ice is not melting, but it is creeping. So it starts deforming, right? And they deform, and suddenly you might have heard that uh, one portion of the Greenland fell in ocean because of because the deformation in that ice and that snow was increased because of the change in temperature, and a little change, a change by 1 degree, plays an important role in the deformation, because we will see that the creep rate increases even if you change the temperature by a very minute amount. The creep rate changes in a lot of materials, and of course in ice it will be very, very high because the creeping temperature is already in negative, and usually we are not at minus 50 degrees Celsius in environment, we are higher than that, so we are already at higher temperature. So that is one thing. Similarly, you can have lead which melts at 200 degrees Celsius. So again, the creeping of lead can happen even at room temperature. So 20 degrees Celsius or 25 degrees Celsius, which is the room temperature, the lead will be already creeping at that temperature. And if you compare this with the steel, for a steel to deform and show time dependence, it will take a very high temperature. So it's a relative thing, and a better way to describe it by using homologous temperature. So you see again that in silicon nitride, the creep is appearing when the homologous temperature is 0.5 or more than that. Here also you see homologous temperature is 0.5, and in the case of ice, which is so at homologous temperature of 0.82, which is much higher than 0.5, the creep is significant. So homologous temperature is a better way to describe the, if you want to compare, for example, the creep of lead and creep of steel, you cannot compare by using absolute temperature. You can compare it by homologous temperature. So now if you look at the testing of creep, we have described this mechanism, but then another type of test. So because creep test will take a very long time if you want to do the test, okay? So that, to avoid that time consumption, you can use another way of testing, where in less time you can predict more or creep properties using the same setup, but you don't uh, waste too much time in doing the testing, okay? So we will now see about this creep testing and stress rupture testing, which is called, in more detail in the next part. Okay.